Hello, everyone. Can you guys all see and hear me? Type in chat if you can. All right, sweet. Okay, so hoping most of you guys here know the drill already. So I'm gonna go ahead and I'm going to paste the link to the folder in chat here in a sec, and then you guys should all be able to. You should be able to, make your shortcut and make your copy of the notebook and things like that. Okay, so there's your folder link. Sorry about the background noise. Can't really do anything about it. So you're gonna go ahead and click on the folder, and then you're gonna go ahead and right click on evaluate ML model.ipynb, and then you're gonna click on make a copy, and then the copy is going to save to your drive automatically, hopefully. And then once you've done that, you're going to go ahead and just open that up. So if I could just get it copied in chat once you guys have done that. And also send a help message in chat if you need help. Have options to add shortcut to drive or download. Okay, let me go ahead and share my screen, and I'll show you what you should get. Okay, application share. Okay, you should be able to see my screen now. So if I go ahead and click over here to evaluate ML model, then basically what we're going to do is you're just going to right click on this file right here, and you click on make a copy. And so when you make a copy, yours should just automatically save to your folder called My Drive. Mine just saves to here because I'm an editor on this folder. And then once you have that, the next thing you're going to want to do is you're going to want to click on this, the arrow up here at the top, and then you're going to want to click on Add Shortcut to Drive. And when you do that, now you go to your drive, and you should have this evaluate ML model folder in your drive with this little arrow here, which means shortcut. As well as that, you should have, your copy of your notebook somewhere in this folder. Then it'll say, evaluate ML model, as you can see, like I have here. And that's the one you're going to be working with for this workshop. But yeah, you would make a copy of the file if I hope I answered that question. Yeah, because you're going to be working with the copy, because otherwise you're not going to be able to do everything you need to do. So to start, just everyone go ahead and open up your mlmodel.ipynb if you haven't already. And the first thing you're going to do is you're going to mount your drive. So you can go ahead and you hit this little play button on the side, or you could also click on the cell and hit Control Enter, and it'll do the same thing. My drive's already mounted, so I don't have to worry about it. However, for you guys, a URL should pop up. You're going to click on that URL, sign in with your Google account, and then you're going to copy the code it gives you. And then you're going to paste it in a little blank box that would appear like right here. Oh, the CSV file? No, you won't need to copy the CSV file. What you're going to do instead is you're going to make a shortcut to the folder, and then that's going to allow you to access this, to read the CSV file directly. So which that's also explained in the notebook. Okay. Can I just get a quick yes in chat if you've mounted your drive? Sweet. Looks like people are generally having their drive mounted. Okay, so if you guys aren't familiar with what I did for my first workshop, just essentially, if you get stuck at any point, just send a help in chat, and I'll try to answer your questions to the best of my ability, and try to make it so that you're able to get the notebook work for yourself. Okay, but without further ado, yeah. So you should have the drive mounted. Next thing you're gonna do is you're gonna make a shortcut in your drive to this folder, which this is the folder I sent out originally. So, well, yeah, just use the link. Just use the original link. Actually, is this one? Yeah, this one doesn't link to the right place. So use the one I sent out in chat originally. I'll go ahead and send that link out again in case there's any people that popped in late. There, so that's the link you should be adding a shortcut to. And then what you're going to do from there is you're going to, click on, just basically click on the name of the folder up here by where this down arrow is, and then you're going to click on add shortcut to drive, and that's all you need to do for that part. And then now you have this direct link to your drive, so we can change directories to there. And so we use, CD, which is for change directory, to drive/my drive/week 3 evaluate ML model. So yeah, it might show you an annoying error message, which we actually silence those here. But yeah, so you're fine as long as you get a statement that looks like this, this content/drive/dot shortcut, blah, 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 /week 3. And that's basically saying like, this line is the same as this line, sort of. But basically, because week 3 isn't like in your actual drive, just a shortcut to it, it goes through this shortcut path in order to get there, and that's why it outputs like that. So assuming no one needs any help thus far, I'm just going to keep moving on. Okay, so we're just going to, import our basic libraries again. NumPy is just basic, some like basic math operation type stuff, matrix operation type stuff. PyPlot, that's just general like visualization of data. sklearn is our ML model, is our ML modeling library, which I believe was covered in the last workshop a little bit. So that's what we're going to be using to generate our models that we're going to base the metrics that we're doing today off of. Which, yeah, if you haven't already realized, this is on evaluating and interpreting ML models. So I apologize for not saying that at the beginning, but yeah. So basically, we're going to first generate our models, and then we're going to kind of evaluate their accuracy using a few different metrics, such as mean absolute error, mean squared error, and root mean squared error. And yeah, and you'll also be able to like see like what those 3 types of error actually mean, as well as true positive, false negative, and true definition. True negative definitions. You'll figure out what those are, which that's just a basic statistic concept. So some of you may already be familiar. And then we're gonna, kind of visualize and calculate accuracy, precision, recall, F1 score. And we're not creating a confusion matrix actually, because confusion matrix, as you'll see, are for classification only, and we don't have our specific data set doesn't really have a feature that we can, or features that we can use for classification really, that would work well, because normally you would want some sort of binary or ternary classification feature if you wanted to do something like that, and we just don't have that here, so we're not gonna worry about that. But I'll make sure to I have there's a link to confusion matrices at the end, but essentially it just says like how often the model is right. Anyways, moving on. Yeah, make sure you import that library, and then you should be able to now load the data. So if you load the data and everything goes well, you should see this. This should all, so this data frame should now pop up, and there shouldn't be any problems. And this should drop a column called unnamed 0, which for some reason goes at the beginning of it every time. And then you should also drop this column, state agency or Indian tribal organization. We're not really too worried about what state this data corresponds to. When we're just, because we're going to basically just feed everything into an ML model like Lucas did for our data. So that's why we're not worrying about it, because state's not really going to help. We just want the numerical values to kind of run the regression here. And then we run df.shape, and that's basically going to just tell us the dimensions of our data frame. So 91 for 91 rows and 15 for 15 columns. Are we just hitting the play button within this folder? Or are we supposed to be using a particular program? So you're literally just, you should just be in the copy, or you should have copied the file yourself over to, yeah, you should have copied the file yourself over to your personal drive, and that's the one you're going to be running. So it should say something like copy of evaluate ML model. That's the one you're going to be running. But essentially, we'll just be, I'd like to make these a little more, lecture style. That way I can get the information across a little bit easier. If we have time, I'll have you guys work on an exercise, and then you can try some of this for yourself. But generally, I'd prefer, and I think you would prefer, to kind of know how to do everything before you try to do it yourself, because I think that'll make it go a little bit smoother. Yeah, no problem. So we now have this, and we have df shape that we've run, so we know the dimensions of our data frame. And so now we're going to basically, what we have here is we're now importing all these scikit-learn specific libraries. And basically what we're doing is first we're going to define our trainings and test sets or whatever. So we have basically our output is going to be average food cost per person. So then to train will be when we're training, we compute the loss value using the training Y, which in this case is the true average food cost per person, and what we're going to be using as parameters to train this model is everything that we have left in our data frame except for average food cost per person, which makes sense because otherwise it would just be able to say, oh, the average food cost per person is this, and then it would instantly get it, which that's not what we want. We want to be able to try to anticipate this. As we looked at in a previous workshop, there's a very low correlation between average food cost per person and any of the other features, which means that we might still get fairly high losses or not the greatest accuracy, I suppose. But however, because we have all these different features, we're hopefully going to try to anticipate it with somewhat accuracy. If we can get like 40-50% accuracy, it'll be better than guessing yourself, but yeah, so there's that. Yeah, so without further ado, we're gonna go ahead and run this. I should also note, if if you didn't catch it before, loss is essentially when you're going through a machine learning model, it's basically, the model is basically going to try to make um, a guess at what the output value should be. However, it then compares to the actual value, and it computes the loss based on that, which is sort of like the difference between these two, or like the discrepancy between these two. And then using that, it's going to, especially when we start getting into something like a neural network here, it will back propagate that loss through the network. Or in other words, it's going to, well, it'll, basically does a bunch of like complicated calculus stuff. And then basically it's going to adjust each of the neurons in our network to, better fit the correction of the model. So over time, generally you'll have a decrease in loss because of that adjustment due to, back propagation and gradient descent. However, that's a bit more advanced. But yeah, you can read up on that if you're curious. Okay, so now we can go to split train and test data. Okay, and we ran that. There's not really going to be just basically setting up our models and fitting the models to the data. So we could run each one of these individually, but generally this workshop isn't about creating the models themselves. That was the previous workshop. This workshop is solely about, evaluating these machine learning models. So, yeah, so now we've created these machine learning models, we need to be able to look at how accurate they are generally. Modeled validation. So yeah, people would make predictions with their training data and compare their predictions to the target values in training data, but that's not what you do. You would compare it to the test data. You don't want, if you're validating based on the same data values that you tested on, you're not going to be very accurate. Or I mean, you'll be accurate, but you're very accurate actually because of a bit of like overfitting almost. It'll make your model look way better than it should if you test on the same values that you train on, which is why we don't do that. We train on separate values to see how well that this model can adapt to new values. That's the most important thing with the machine learning model, is that we get rid of overfitting to the best of our ability, in order that we can, kind of be able to anticipate new values, which is going to be our test values, based on what the models have learned from training. Right. Okay. Error metrics for regression. So the first one we're going to look at is mean absolute error. Mean absolute error, I think, is fairly self-explanatory. It's, it's just the actual minus the predicted, and we make it absolute value because it's a magnitude rather than, positive or negative, because we don't want it to because a negative and a positive error are both still errors. We don't want to have them cancel each other out and say there's no error. So we want to take the magnitude instead. And then you would just add all of them up and divide them. So that would basically give you the average error of your, the average error of the sums of these magnitudes, essentially. And so to calculate it, we first need, or we're just going to use one of the models we had earlier. So for this one, we're using linear regression. So we say lr.predict. Remember, we fitted all of these up here. So you wouldn't technically have to run lr.predict again. You could just use this variable called linear regression predictions. And if you wanted to use another one instead, you could say svr.fit. Well, this one actually doesn't have a prediction one, but you would say svr.predict, x test, and it's going to give you the prediction values based on that. Yes, and for neural net predictions, you can just use this variable neural net predictions, or you can say MLP regressor dot predict. And then for decision tree, the same thing, dt.predict or decision tree predictions. It's the same exact thing. It's just if you use the dot predict, you're essentially running the predictions again. And remember, our x test is just our test values. This is what we're using to evaluate our model. We're not actually training on this. So we're not going to get better results every time. That's why the number is the same no matter how many times we run it, or generally the same no matter how many times we run it, is because it's not training the model when you use it to predict, because we're not computing the loss. We don't know how accurate it is. This is just our prediction based on how good it is. And so for each one, it's calculating it is, however, calculating the difference between our y test, which is, the actual values, and our x test, which is what we're using to predict. So you see we have y test, and then we have our predicted food cost as our metric. So this is what we're predicting, and this is what is actual. And so using that, we take yi, our y test, minus our predicted food cost for every single value in those sets. And then we plug it into this formula, and we calculate the mean absolute error, which in this case is 8.4, which is, decent. Well, it really depends on the context to know if it's decently big or not. So if we look at cumulative food costs, it's generally decent. I think that's generally decent performance given what it's average food cost per person. That's right. So you see, because we're looking at average food cost per person, you'd see for something like this, that's about 8/48 or something like that. So that would be 1/6 is 23% or something like that, if I remember correctly. But yeah, so generally that's about a 23% error on average-ish. Now, that's just very rough calculations, obviously, but generally it's close, but it's not way far away, but it's not the perfect accuracy either. You would get training on an MNIST data set, which is the handwritten number data set, something basic like that, on a proper neural network with proper back propagation and all that, running for 10 epochs with a 3x3 convolution or something like that. We're not doing any of that, nor do we have a very large data set. We're only working with 91 rows. So it's anticipated that either it's going to overfit or it's not going to be very accurate because we don't have a lot of data, which that's fine for this. The main point is that you know how to do it, so that when you are working with a different data set, hopefully you want to find one with a lot of data points, and you'll be able to use that and make more accurate machine learning models, and also be able to test the metrics. But generally, yeah, the smaller your error is, the better. Okay, and next we'll look at mean squared error and root mean squared error, which these are very, very similar, obviously, and they look the same. So mean squared error is essentially something that's going to penalize you more for the farther a singular value is away, because you're squaring the difference, which is that's a pretty massive difference if you think about it. So a difference of 2 now becomes 4, because you're squaring it each time. So then it's a lot more significant the farther you are away. If you're really close, if you have 0.1, if you're 0.1 away, then it's then you square it and you get 0.01. So you're generally pretty close, so the error is a lot smaller. However, if you're really far away, like if you have a difference of 4 or something, that difference now becomes 16. And then, however, that's not even the most popular. The most popular is root mean squared error, which kind of it essentially just takes the square root of the mean squared error, and that kind of standardizes it a bit more. But it's very similar concept to the mean squared error, where still the farther you are away, it's still a higher magnitude, because even though we're taking the square root, because we're taking the square root of everything, the ones that are farther away are still going to be penalized more. It just not as drastically as they are in mean squared error because of the square root. Okay, now we're going to generally check how our model's performing. So yeah, like you can read here, context is everything. So like, right, and RMSE is 10 of 10 is fantastic if you're predicting the price of a house, but if you're off by $10 on the price of a candy bar, I'd say it's probably pretty terrible. Yeah, so now we're going to basically, well, we create this dictionary, which is basically linear regression, which we're defining these as what they were earlier, essentially. So defining these based on what they were earlier, or what the predictions were earlier in our chart, we would just run this, and we have this definition, or this function definition, generate metric, which essentially, we have our dictionary here of, or our list, I suppose, of, our mean absolute error, our mean squared error, and a root mean squared error. And we're going to calculate mean absolute error just using this mean absolute error function through scikit-learn. As you can see, we've imported from here. And then we'll use mean squared error, calculating it, for this I just did y-test versus predicted food cost, and this versus, so generally, the reason, so you'll see, if you'll notice down at the bottom, you'll see that they're all the same. This is due to a slight error in the code, or an error in the way that this was coded. So essentially here, instead of predicted food costs, you're going to want to have, either the model.predict or something along the lines of, that. So here we had predictions. So if I were to do predictions instead, and then run all of these, then it should theoretically, have different values. So let's try that now. And if this doesn't work, we have some time. And I can either try to bug fix, or we can move on, which I don't think it'll take me that long to bug fix if this doesn't work. Okay, and if we run that, we see we get a type error, expected sequence or array-like, got a class at svr. So this is for here. Okay. The way that SVR was coded up here. So we're going to go ahead and do, so we're going to so we'll do, so we're going to take SVR, and we're going to, so we'll still have our fit, right? Which that's always going to be the same. However, SVR predictions should really be SVR dot predict X test. Okay, and now when we run that, now this is our proper predictions. I believe this was the one that was giving it trouble, if I remember correctly. given if you're bug testing, it won't always go this smoothly. But yeah, now we have, there we go, boys. Now we have, and girls. Now I suppose we have all our correct values, and you can see by the differences here that now we have the mean absolute error, the mean squared error, and root mean squared error for all these different values. And so you can kind of also compare like how well they all performed versus each other, which yeah, looks like if we look at it, our neural net's pretty stupid. That's mainly due to the fact that there's so few values for it to train on. Neural networks tend to work best with very large data sets because they can really fine tune over time and over several epochs, which an epoch is just, an iteration through the data set. Whereas linear regression, SVR, and decision tree don't necessarily need that to do decent. And we see linear regression generally does the best with what we have here. Yeah, neural net's just stupid large for no particular reason. But yeah, so that would definitely get better if we were working with a couple thousand values instead of like 100 values. Neural net would eventually outperform the bigger the data set got, probably. Like it really depends. It might just totally overfit the data set, which that could be pretty terrible. Which when you're working with big data sets, you also want to note that you should probably have a validation set if you're working with a neural network. And essentially the point of a validation set is if your model looks like it's gotten too close to perfect, then there's a very decent chance that you've overfit the model. So then what you'd want to do is you would want to test it against our validation set, which is a set of data that's different from the test set. It doesn't have to be very big. You just test it against this other set of values here. And if it's like way, way, way off, then you would say that then you would want to, like go back through and like retrain the model basically, because that means it overfits. So you need to go back so that it becomes more adaptable, or either that or you would stop when the validation set has the lowest loss or the best performance. But yeah, generally in this case, it looks like linear regression and SVR did the best. You can see, well, SVR has a lower mean absolute error. Linear regression has the lowest RMSE and MSE, and that's due to sort of just the way that SVR works generally, where it kind of like you're either like on one side or the other of this. You're either kind of like on one side or the other, but yeah, generally you can read more into SVR to learn about how exactly it predicts. But essentially, yeah, these errors mean that there were slightly like farther away values in SVR than there were in linear regression, which means linear regression fit a line that's a little bit closer. Not by much, obviously, but just a little bit. Not very good for the data set because, we have an insanely high error. So we're just going to ignore the neural net in this case. It might be a sin. If you guys are CS majors, you might think it's terrible to ignore the neural net, but in this case, it's not the worst thing you could do. Okay, so now we're getting into some statistics stuff. So we have true positive, false positive, true negative, and false negative. So true positive, if we're talking about, this has a lot more to do with classification-based ML models. However, what we did earlier was regression-based, or kind of like being able to predict values based on previous values. whereas this is classification. So this is the same as like, like trying to get a model to find the difference between handwritten digits, as you'll see in something like the MNIST data set, or something like trying to find the difference between a picture of a dog and a cat, or, trying to find the difference between an email that you're actually going to read and a spam email. Which if you read into it, it's actually it can get a little bit creepy if you look at how they classify, start to like learn how to classify spam email, because basically when you classify something that went to spam as not a spam, it then uses that and it goes back through and kind of like updates, and as like it's like its own sort of like machine learning model to an extent. It's kind of cool, but also a little bit creepy. So a true positive is going to be, if we're looking at the example of emails, it's going to be an email that was spam that we correctly flagged as spam, or the email system correctly flagged as spam. So something that is truly accurate, and we'll say it's positive for being spam, basically. So where we take positive as our spam, if the model correctly classifies it as spam, that's a true positive. And then for a false positive, it's going to be some email that, isn't actually spam, but goes in the spam folder anyway. And that's a false positive. False positives, there's always going to be false positives, and there's always going to be false negatives. That's just not something we can help. If you take statistics, or you've taken statistics before, then you'll know it has a little bit to do with things like the alpha value and things like that, where it's basically like the farther you go in one direction, the more likely you are to have a false positive, and the more you go in another direction, the more likely you are to have a false negative. And it would just depend on like the metrics being used, really. But yeah, you'll learn more about that in statistics if you haven't taken it already. Okay, and then just general accuracy metrics. Here's some other ones we can look at. So precision and recall, they both involve these quantities that we looked at earlier. False negative. I should also note, false negative obviously is a spam email that it's when we take spam and we say, oh, this isn't spam in our model. And that's obviously a false negative, because spam is spam. Spam is spam. Sorry, I get distracted sometimes. And then true negatives would be a not spam email that we correctly classify as not spam. And so obviously the ones you really want are the true negatives and the true positives, because if we have all true negatives and all true positives with 0 false positives and 0 false negatives, then that means we have an 100% accurate model. And thus, the less false positives and false negatives we have, the more accurate our model is. So precision and recall is based off of that. So essentially, precision is based on, calculating this proportion of positive identifications and how many of those were correct. So of all of the so in this case, in all of the emails that we had that we classified as spam, so we're going to look at the true positives, the one that were actually spam that we classified as spam, divided by the total number of emails that we classified as spam. And that's how precise our model is when we're looking at a classification model. So, if we have, like I said earlier, if we have 0 false positives, then this is 1, where 1 would be, 100% accurate, essentially. However, if we have, 1 true positive and 2 false positives, then it's going to be 0.33 or 33% precision. And so obviously, the closer you get to 0, the worse it is, which it is possible to get 0, but also extremely unlikely. But yeah, you'd obviously get 0 when you have 0 true positives and any number of false positives, or if you have infinitely more false positives than true positives. But that's just a basic proportion, essentially. And then recall answers a slightly different question, which is what proportion of our actual positives were identified correctly? So if we look at all the things that should have been spam, basically. So TP is our true positives. It's what we've classified as spam through our model. Or that's what we've classified as spam through our model that's actually spam. And then we're going to go ahead and we're going to divide that by the sum of all our true positives and our false negatives, which this is actually the total true number of spam emails that got pushed through our model. So in this case, all right, so in this, right, so we're working with spam emails. So if you have, if I have 10 total spam emails that it pushes through my system, okay, then we'll say, and we say we correctly identified 3 of those spam emails as spam. So then this would be 3. And inversely, we would have 7 false negatives if we had 3 true positives. So we'd have 3 over 3 plus 10. This is our total number, or 3 plus 7. So this would be 10, because this is essentially our total number of spam. So the number correct, 3 over 10. So we'd have a 0.3 accuracy, or a 0.3 recall, I suppose, or which is 30% recall. And you can then see as you get close to the threshold, basically your model just tries to draw this line, and anything on one side of the line, or as you get very close to the threshold, you start to lose accuracy, and that's what you'll see here. So if you had something like a dog that looks like a cat, or a cat that looks like a dog, where they have very similar features or something like that, which does happen, which is why you never have 100% accuracy with these models most of the time, then you'll see, I'll see a red dot on the wrong side of the line. So because this is a false positive, where it really should be a true negative and be on this side, So essentially, as you get closer to this classification threshold, you see we have green values on the wrong side and red values on the wrong side, where we would, we want all the red values to be on this side and all the green values to be on this side if we wanted 100% accuracy. However, these ones speckled through is just kind of what you get with that kind of precision versus recall thing. And we'll see again here, looking at all the true negatives. We have some false positive mixed in, and some false negatives mixed in over here. So, none of it's perfect. The more data points you have from a wide and varying data set, the more accurate and adaptive your model is going to be. And there's even cases in which you would train on multiple data sets, though that's far less common. And then the last thing is, just this general idea of a confusion matrix. We can't, like I said, for the same reason that we can't run any of these other classification-based metrics, because we don't have any sort of classification feature in our data set as of now. We can't do a confusion matrix, but essentially a confusion matrix is as shown here, where, you have your predicted and your actual. And so where these line up, those are going to be, your true positive, and these can be your true negative, where positive would be cat and negative would be dog. And then these are going to be your falses, or your false positive, and your false negative are going to be the ones that were, inaccurately classified, essentially. And so generally you'd be able to use scikit-learn's confusion matrix function as identified here, and be able to do something like just, which this would be something like a Y test and, uh, a Y. So one of these would be a Y test, and the other one would be like the prediction of that specific model. And then we would run confusion matrix, Y true, Y predict. And it would give us this matrix, which kind of generally explains like how accurate it is, or like kind of like which ones were identified correctly and which ones weren't. And you can also see it being done with kind of this idea where you have these labels. And so when in the case of you having labels, well, we can ignore these top two, but um, essentially when we have these labels, it then just allows us to like, have display like the words ant, bird, and cat on the side and on the top. And so you like actually see like what the confusion matrix entries correspond to. But yeah, that is the end of our workshop. I'll stick around for a bit for questions if you guys have any. But other than that, I thank you all for coming.